A simple coil of wire. It has this secret life. It's one of the most basic components in electronics, but it holds this incredible power, especially when you throw alternating current at it. So let's unravel the mystery of the inductor, shall we? So here's the big question, right? How can this one little component be a total pushover for one kind of electricity, acting just like a plain old wire, but then suddenly turn around and put up a huge fight against another kind? It's like it has a split personality. And that's exactly what we're going to figure out today. Okay, so when you're dealing with direct current, DC, an inductor is, well, it's pretty much invisible. The current just zips right through. But switch over to alternating current, AC, and all of a sudden it starts pushing back. And here's the really weird part. The faster that AC signal wiggles back and forth, the harder the inductor pushes back. Wild, right?
Visit youtube.com/avidsystem and don't forget to subscribe.
So what is its trick? How on earth does it do that? Well, the answer is all about this fundamental force that every single inductor can create. All right, the secret sauce here is something called back EMF. So think about it. When current flows through that coil, it creates a magnetic field. Easy enough. But with AC, the current is always changing direction, right? That means the magnetic field is constantly growing, collapsing, growing, collapsing. And all that change actually creates a second voltage in the coil, a voltage that pushes back against the original current. And that is the absolute key takeaway here. An inductor doesn't fight current itself, it fights the change in current. The best way to think about this is like inertia. Like trying to spin up a really heavy flywheel? It fights you at first, right? It resists getting started. And once it's spinning, it resists slowing down. An inductor does the exact same thing, but with electricity. It wants the current to be stable and steady, and it will absolutely fight you if you try to speed it up or slow it down too fast. So this electrical inertia isn't just some vague concept. Nope. It has a proper name, and we can actually measure it. Let's meet the star of the show. We call this opposition inductive reactance. Its symbol is XL. And get this, it's measured in ohms, just like resistance. But here's the big difference. Unlike a simple resistor that fights everything, reactance only shows up to fight alternating current. And it wouldn't be physics without a formula, right? But don't worry, this one's pretty simple. XL equals 2 times pi times F times L. Now that 2 pi part, that's just a constant. It's there to make the math work out with all the waves and cycles. The two parts you really need to care about are F and L. Let's break those down. First up, we've got F, which stands for frequency. This is really the heart of its whole AC trick. The higher the frequency, the faster that current is changing. And the faster it changes, the more back EMF the inductor creates to fight back. So more change equals more fight, which means higher inductive reactance. It's that simple. And the other piece of the puzzle is L for inductance. This is all about the physical inductor itself. How many coils of wire it has, what's in the middle, how big it is. A bigger, beefier inductor with more coils is going to create a much stronger magnetic field. It has way more inertia, so it puts up a much bigger fight, which means it has a higher inductance, and that leads to higher reactance. Okay, so this constant tug of war between the voltage trying to push through and the inductor's back EMF pushing back, it has another really interesting side effect. It completely messes with the timing of everything. It creates a delay, and not just any delay, a super specific, super precise delay of exactly 90 degrees. So what on earth does a 90-degree delay mean? Well, in a perfect world with a perfect inductor, the current is always playing catch up with the voltage. The voltage peaks first, and then the current peaks a little later. It's always lagging behind by exactly 1/4 of a full cycle. So remember this, voltage leads and current follows. And why does this happen? Well, it all goes back to that idea of inertia. The voltage from the power source has to build up all its strength. It has to reach its peak just to overcome the inductor's stubbornness and get the current moving. You have to put in the effort first before you can see the results, and in this case, the results is the flow of current. Okay, let's clear something up. We've got resistance, and now we've got this new thing, reactance. They both fight current, and they're both measured in ohms. So what's the actual difference? This is a really important distinction to make. All right, check this out. Resistance, SR, it fights all current, Doesn't matter if it's AC or DC, it just gets in the way. Then you've got reactance, X. This is the new guy, and he only cares about fighting AC. And when you have both of them in the same circuit, their combined total opposition is called impedance with a Z. That's the total roadblock that an AC signal has to deal with. Okay, so this is all pretty cool theory, but let's get real. Why does any of this matter? What's the point? Why is this behavior so incredibly important in electronics? All right, let's do a quick recap of the essentials. 1. Inductors hate change. 2. We call this opposition inductive reactance. 3. That reactance goes up as the frequency goes up. And 4. This whole battle makes the current lag behind the voltage. You get those 4 things, and you've got the foundation for thousands of different circuits. Because the inductor's opposition is totally dependent on frequency, it basically acts like a bouncer at a club. It lets the low-frequency signals just waltz right in, no problem. But when high-frequency signals show up, it puts up a huge wall and says, nope, you're not getting in. This makes it the perfect tool for building filters. Think about the speakers in your sound system. An inductor can be used in a low-pass filter to make sure all those deep, low-frequency bass notes go to the big woofer, while blocking the high-pitched stuff from getting there. And there you have it. We've cracked the code. The inductor's secret is out. It's not just a boring coil of wire, it's this amazing dynamic gatekeeper that's sensitive to frequency. So now that you know this, now that you know you can selectively block or pass signals just based on how fast they wiggle, what kind of awesome circuits could you design with that power?
Thanks for watching.